All right, so welcome back. So we're gonna try example 8, and this example we're gonna begin applying the concept of absolute max and absolute min into real life problems. And so we're gonna use all the tools that we have discussed before to be able to determine the absolute max and absolute min of the problems, depending on what they're asking us. So let's consider a function that is a cost function of x that equals 6400 plus 510 times x plus 0.9 times x squared. And then the demand function is p of x, which equals 1530. And they're asking us to find the production level that will maximize our profit. So a lot of things are given and a lot of things are not given. One thing that's not given, and they're asking us to maximize the profit, that means that they're asking us to find the absolute max. And if you notice, they're not giving us the interval for which this is going to happen. We can argue that this should be greater than 0, right? Because x needs to be it's a quantity, so it only makes sense you can produce positive quantity. It doesn't make sense to make negative quantity. So anyway, but we're not given an interval, so we're gonna have to do a different approach at some point to determine that this is actually the maximum profit. All right, so we're gonna jump in to think about what is they're asking us to do, right? What are they asking us to maximize? And I'm gonna underline there. They're asking us to maximize profit, but the profit function is not given to us. So that's another thing we're gonna have to try to find. But we do know how to find it, right? We have a clear understanding that the profit function, which is uppercase, is equal to the revenue minus the cost function. Now we are given the cost function, right? So we are given cost function to be 6400 plus 510x plus 0.9 x squared. But we're not given the revenue. But we are kind of know how to find the revenue. We know the revenue is quantity times price of selling your item. So the demand function is in fact the price of selling those units. So actually this is the price. So that means that in this case, x, of course, x represents the quantity. So we have the revenue is equal to, maybe I'll write it over here, x times 1530, right? So in other words, revenue is equal to 1530 times x. So now we have everything we need, right? Let's underline a few things here. Let's highlight the fact that we know that the cost function is this and that the revenue function is this. So what we're going to do here is we're going to take those two to find the profit. So let's replace r of x with 15 or 1530 times x minus the cost function, which is 6400 plus 510x plus 0.9 x squared. Now, of course, we have to put parentheses. We have to put the parentheses every time you replace a function with its expression. Every time you do a direct substitution, that's a very proper thing to do. And that's also going to save you from making silly mistakes, meaning that you may forget to distribute that minus to every single term. So we have 1530x minus 6400 minus 510 times x plus 0.9 x squared. Oops, that's a minus. Right, that's a minus. So if we combine like terms, we're gonna note that we're gonna end up having negative 6400, and combining these two terms, we end up getting positive 1020 x minus 0.9 x squared. So this is our profit function, right? So this is a profit function. This is what we're trying to maximize. So we're gonna have to find what we did before. The critical numbers. We don't have an endpoints here, so we're gonna have to take a different approach. So nonetheless, we still gotta find the critical number. So find the critical numbers. We know that that happens whenever the derivative is 0 or whenever the derivative is undefined. But we already know that this is a polynomial, so this is always going to be defined. Sorry, that's not. That's the original function, but we know that it's going to give us a derivative for which is going to be a polynomial. So let's go ahead and find the derivative. So the derivative of p is going to be the derivative of the constant term negative 6400 is going to be 0, so we're not going to write that out. The derivative of 1020x is going to be 1020, pretty much drop the x. And the derivative of minus 0.9x squared by using the power rule along with the constant multiple rule tells us that we multiply these two together. This gives us 1.8 times x, and then we subtract 1 from the power, which means it's the power of 1. But of course, we never write that out. So like I said before, this is a polynomial, so it's always going to be defined, so therefore this is never going to be the case. We're never going to be able to get a critical number by making this undefined, because it's never going to be undefined. Thus, we have to find the critical number by finding when is derivative equal to 0. So all we gotta do is set this equal to 0 and solve for x. So how do we solve for this? We're just gonna say, well, it's 1020 minus 1.8 x equals 0. We add this number on both sides of the equation, and we end up getting 1020 equals to 1.8x divided by 1.8, and we end up getting that x is equal to roughly about 566.666, right? Which we're gonna probably round up at some point. But this is the quantity that we need to produce. Now we're not sure whether this is going to be a maximum profit. It could give us a minimum profit. We could quickly argue, because we already know this is a polynomial with a positive degree. We know it's gonna be it's over here. We know it's a polynomial of negative degrees. No, we know it's gonna look down, so it's gonna go like this. But we're gonna actually be able to also show it by making a quick number line. Right, so we're gonna do 566.66, and we're gonna test a few numbers on the left side and on the right side. We already know that the derivative value at quantity 566 is gonna give us 0. What we need to do is check what happens on the left side and what happens on the right side. So just try a few numbers that are easy to compute. For example, 1, and let's just try 600, right? So we're gonna figure out what is whether this is a plus or a minus, So where do we compare that? At the derivative function. And we know the derivative is 1020 minus 1.8 times x. So whenever we have a prime of 0, we end up getting, this is 0, so that gives us a positive 1020, right? We don't care that it's actually 1020, we just care that that is a positive value, right? We care as a positive value. And then, sorry, and I meant to plug in 1. So 1 here, still gonna give us a positive number. Then we're gonna plug in 600. So let's see what we get from here. From here we get that 1.8 times 600. That's 1080, which is going to be a negative number. There you go. There you go. There you go. So what do we know? That the profit function is actually increasing, and then it comes horizontal, and then decreases, right? So what do we know? It is in fact a local. This will give us. This is gonna be a look. This gives us a location of a local max. Now, since there's only one critical number, we know that and this is local max. We know that we have in our table, it says if the function has only one critical point and is a relative extrema, then it's also going to be an absolute extrema. So because there's only one critical number and this happens to be a local max, then this by definition will give us a global max, right? That's going to tell us where we have a local max. And the question, let's go back to the question. It says find the production level that will maximize the profit. So that means that we're gonna have to produce 567 to produce 567 items to get a absolute max, right? In other words, to have a maximum value of profit. All right, and there you go, right? So everything is all fitting together now, and it's important for us to keep track of all the tools that we have learned before, and so that we can apply this in the corresponding problems. All right, so that's it for this example. I'll see you guys next time.